Freedman. His title is Manifold, Pairings, and Quantum Gravity. Thank you, John.
Thank you all for coming. So what I'd like to spend the hour doing is describing a mathematical idea that I hope might have some utility in quantum gravity. So most of the talk will be on different preliminaries. So the first will be what I'll call universal TQFT, topological quantum field theory, which also goes under the name manifold pairing, and you'll see why. The second, I'd like to discuss something called causal dynamical triangulations, which is a combinatorial approach to quantum gravity where the metric is simulated by a combinatorial structure or triangulation. But the word dynamical means that somehow Lorentz geometry is built into this. And the third topic is what I call two-field theory, which the two doesn't mean two-dimensional field theory. It means two is in like two categories as opposed to one category. Something like this might be called third quantization. And then try to put these together to describe an action on some things that I'll call formal chains. Which I will argue should concentrate somehow on 3+1 dimensional space-times. So the idea of the whole thing is to grab some mathematics from here and there and come up with an action so that the action is agnostic as to dimension. You can throw things of any dimension at the action, but by some kind of stationarity property of the action, it'll concentrate in 3+1 dimensions. And of course, you could say I'm behind the times, the universe is not 3+1 dimensions, haven't I heard? Well, there's actually some hint of small dimensions that you can extract from this approach too. So let's begin with universal TQFT. So before universal TQFT, let's just have an example of a TQFT. And since this is the Simon center, the best example would be Chern-Simons theory. The Chern-Simons invariant of a three-manifold, giving rise to a partition function associated to a three-manifold. So Chern-Simons theory generally takes as input a lead root G and a level K, so I'll do that. And then I'll define this, the partition function of the three-manifold to be this physics thing, the integral over the space of all connections with e to the minus 2 pi I over k, that's the level, of a sensible integral, which is the integral over the three-manifold of ADA plus 2/3 A cubed. So this is, we're imagining that over the three-manifold we put a G principal bundle and A is some connection in that bundle, and then we choose section locally, or actually globally, to think of the connection A as actually the algebra value 1 form. Then this integral makes some sense, but it has some ambiguity which is removed by this exponentiation. And this K is called the quantization level. So, you know, what you see when you look at this example of the TQFT. Oh, and what's important is the metric did not enter the formula, which suggests that this is a topological invariant. Okay. Now, of course, that's not the end of the discussion, is because you don't see the metric. Maybe you need the metric when you regularize the integral. You know, so it's actually non-trivial that the metric's not important. But that's the meaning of topological invariant, that the metric should not be important. That's the T in topological quantum field theory. Now, if you want to go home and invent your own field theory, you have to be clever, because you have to think of some action that's going to be topologically invariant. But mathematicians like to do things universally, and this universal synonym is lazy. So I'm going to tell you the lazy TQFT, where you don't have to go to the trouble of inventing the Chern-Simons action. You might not be as smart as Chern or Simons. But anyone can come up with the universal example. So in order to make the universal TQFT, we'll take the complex numbers, which is where this action resides, and we'll replace it with the ring of all d-dimensional manifolds. 3 will not be important now. Well, D is a parameter. We'll consider our manifolds up to diffeomorphism. So what is the ring of closed d-manifolds? Well, addition in the ring is formal. You can multiply a manifold by a scalar. It's really an algebra over the complex numbers. We multiply a manifold by a scalar, and we can just take formal linear combinations. That's plus. And times is disjoint union. So the, let's see, the additive, what's the additive and multiplicative units? Well, disjoint union with the empty set doesn't change the diffeomorphism type, so it's the empty D manifold, which is the multiplicative unit, and 0 times all coefficient manifolds is the additive unit. So there's our coefficient ring, and now it's pretty easy to come up with a topologically invariant partition function. We'll say Z of the manifold of dimension D is just that manifold. So the main ingredient in the TQFT is what's called the Atiyah axiom. So let me explain that to you. So let's go back to Chern-Simons theory for a moment. In Chern-Simons theory, we have a 3 manifold, and we associate it to it's a scalar. If we have a surface, we associate it to it a vector space. And if we have the surface bounding the boundary of the 3 manifold, then this 3 manifold determines a vector, which I'll just call bracket M, inside the vector space of the surface, the Hilbert space of the surface. So the Atiyah axiom says that if I have a closed manifold that's divided into 2 pieces, A and B along a surface, then the partition function of the union is the inner product in this V, this Hilbert space, of the associated pieces A and B, thought of as vectors inside the Hilbert space. If you cut something into 2 pieces, each one gives you a vector. You might think of a vector and a covector, but since it's a Hilbert space, I won't worry about that. And the gluing together corresponds to the dot product. So it's this structure in a TQFT that we want to preserve in the, or reflect in the universal TQFT. So I already told you that in the universal case, Z of the manifold manifold is just the manifold. This is in dimension D. What about in dimension D minus 1? Suppose I have a manifold of dimension D minus 1. Well, I'll associate to this, it won't quite be a Hilbert space, but it'll be a vector space. And it'll be formal linear combinations of manifolds in one higher dimension, such that the boundary of that manifold is identified with the manifold of one lower dimension. This is finite linear combinations. Now the T axiom will give a pairing. Is consistent with this pairing, which is if I consider two different vectors in here, V and W, so let this be summation AI, capital AI, and this summation Bj, capital Bj. So this is linear combinations of manifolds bounding this surface, so to speak. Then the inner product, VW, will be, by definition, it's going to be a sesquilinear form, AI Bj bar, AI Bj bar. I put this part here as complex conjugation and this part just to remind us that we should reverse the orientation on the right piece. So here the inner product, or the pairing on this universal vector space is obtained by taking the process of gluing manifolds together along a hypersurface and extending linearly on one side and conjugate linearly on the other. And actually, if you look at papers from 10 or 15 years ago, BH and B construction and so on, it's actually easy to draw a commutative diagram and see that all the Rusheltine-Turiev, Witten, Hilbert spaces in the literature are quotients of this universal one. Okay, so I want to tell you basically what the facts are regarding this pairing. And this has been the result of several collaborations with mathematical friends of mine. So roughly the situation is that the facts that relate to dimension 3, D equals 3, are with Kevin Walker and Danny Caligari. The facts in dimension 4 are with Slingerland, Long, Walker, and and in dimension greater than 4, Peter Teitner and Kreck. Okay, so these credits aside, let me tell you what the facts are. The facts are that for D less than or equal to 3, all the pairings, so I need to put a subscript and tell you what D minus 1 manifold goes down here, so that's the variable. All pairings are positive. And what positive means, by definition, is that if you pair a vector with itself and you see that the outcome is 0, that should imply that the vector is 0. And then for D greater than or equal to 4, most, or many, let me say many, and as far as we know, possibly all, it's open, pairings have, in contrast, light-like vectors. And it's these light-like vectors that I want to arrange in action I want to arrange an action just with these like vectors will put a sort of stop to the dimension of space. So this is a little bit abstract. Let me do an example to make it quite concrete. So I want to do an example in the extremely low dimension. So let sigma d minus 1 be 0 dimensional, so d is 1. So this will be just 4 points. I won't worry about orientations in this picture. And I'll let it bound two different manifolds. I'll let it bound this manifold, which I'll call A, and I'll let it bound a different one manifold, which I'll call B. And then let's compute the inner product of A minus B with itself. Well, this shouldn't come out 0 because we're in the low dimension. It would be a like vector if it came out 0. So it should have 4 terms by linearity. So if you pair yellow with yellow, you'll get 2 circles. If you pair yellow with pink in either order, you'll get some picture like this. I'm trying to draw exactly what you would see if you kind of flipped one of the two over and stuck them together. And if you pair pink with pink, you'd get this. So this would, you're supposed to collect terms according to diffeomorphism type. So the answer to this pairing, remember, it lands in this funny ring of manifolds. It's 2 times the disjoint union of a circle with itself minus 2 times the circle. That's what it comes out, which is not equal to 0. You can't collect any further since these are different types. Now, you may be wondering how you could get 0. Well, this example kind of helps you understand that, because if these 4 diffeomorphism types had been the same with these different signs coefficient, they conceivably could cancel out. And that's exactly what happens in dimension 4. It turns out when d equals 4, there's an example with the Mazur manifold, which is a homology 3-sphere, and it bounds 2 different contractible 4 manifolds, A and B. And these contractible 4 manifolds are different as they're attached to the boundary. They're a different real boundary. And when you compute the pairing, A minus B paired with itself, these 4 combinations occur. And now it's not obvious because we're working in the smooth category. There is no known smooth 4-dimensional Poincare conjecture. But direct calculations with these examples shows that all 4 are diffeomorphic to the 4-sphere. So the analogous expression just turns out to be S4 minus S4 minus S4 plus S4, which is 0 times S4, 0. So that's how things cancel. So since I didn't state it explicitly, I feel now, since I've dragged you through this example, I do owe you an exact definition, which is, how do you tell, what does it really mean to say the 2 things are different? 2 D manifolds with the same boundary are different. What does that mean? Well, the definition is this, that if we have sigma D minus 1 and we include it into A as its boundary, and we include it into B as its boundary, then if there's a diffeomorphism here, making this diagram commute, that is, the diffeomorphism extending the identity on the boundary, then we call A equivalent to B. Okay. So we already saw in the 0-dimensional example, so to speak, at the top of the board, the A and B, someone might argue, were the same bounding manifold because they're each 2 intervals. Those are diffeomorphic, but you see, they're not diffeomorphic to each other, rel the identity on the boundary. So that's the correct notion. So for example, intervals attach in many different ways to points. A solid handle body attaches to a surface actually in infinitely many different ways. This cosets probably with the mapping class group divided by the subgroup that extends over the handle body. Okay, that's the first topic, universal pairings. Now let me go to this causal dynamical triangulations. Oh, maybe I didn't set an eraser down. Maybe I didn't have one.
There should be one inside the lectern.
Ah, there it is. Okay, so as I mentioned, there's a long history of trying to manufacture something that looks like the universe statistically from triangulations. Actually, the very simplest thing you could do if you wanted to make a two-dimensional universe, this two-dimensional Euclidean universe, is you might try all triangulations of the sphere, say, with n simplices, and let n go to infinity and weight each triangulation equally. People have studied that example, and it's called the, if you take a base point, it's called the random plane. And Godad, Schramm, and some of his students worked on it. Turns out the random plane has Hausdorff dimension 4. It's basically governed by a pair of independent Brownian motions. So it doesn't come out looking like kind of a, doesn't look anything like a plane. You might hope that the measure somehow concentrated around Euclidean planes and fluctuations, but it doesn't work that way. So people have experimented in higher dimensions and in dimension 2 by adding, by using some non-trivial action to try to separate out the cases. And typical sort of thing to write down for an action is the integral of scalar curvature plus a cosmological, actually minus scalar curvature, plus a cosmological constant. And actions of this kind with various coefficients between the two have been explored, I'd say rather unsuccessfully over about 40 years to try to find universes which fluctuate around Euclidean space. If you study this particular action, typically what you get are what they call collapsed phase, where the universe has infinite Hausdorff dimension, and it's just kind of a tight little ball, or you get something called branch polymer phase, which also doesn't look like Euclidean space. So I think a breakthrough in this was made by what I think of as the Utrecht group or school. There are many papers on the archive by Amjorn, Wall, Jerkowitz, in various combinations. And other collaborators. And what they did is, instead of working entirely in the Euclidean version of the problem, they explicitly work with Lorentzian simplices and build spacetimes that have a foliated structure in them. So the picture you should think of for their work is they start with a d-1 dimensional space with a triangulation, and then they randomly create a layer. So I'm just trying to do something that looks pretty random here in terms of how the vertices are paired. But the important thing is that and then they would create another layer, and create layers. And then each layer, it's presumed that every individual simplex in such a picture has length 1 in the space-like directions, and length squared, a negative number, which they call minus alpha, in the time-like directions. So these are not quite equilateral. There's this parameter alpha, and there's a difference between time and space. But you can use your Lorentzian trigonometry to look at the glued up thing of simplices, and around the codimension 2 strata, you can calculate the angle defect, and then that's this Regge calculus. If you integrate over the 2-dimension strata the angular excess or defect, you get a kind of combinatorial version of scalar curvature. And of course, as Hilbert showed that scalar curvature was the correct action for the Einstein equation. So this is a combinatorial effort to reproduce that.
You don't really go into, add anything else?
No, it seems to be where it concentrates. And then they were quite successful. I mean, there's no proof, but if you look at their papers, they get numbers like 3.9 or something like that, instead of 4 for the Hausdorff dimensions of the things they build randomly. So they seem fairly successful in having a random construction that comes up with things that look like de Sitter space.
How does it fit that out?
Oh, it does. So just like in the previous efforts, I said there was like a crumpled phase and a branched polymer phase. Alpha has to be tuned to find the right place in the phase diagram. And so does the cosmological constant. So there's a fair amount of tuning to make this work. But there seems to be an open domain with parameters that gives them reasonably good spaces. Okay, so come back to this very soon. Now the last sort of ingredient is what I called two-field theory. So, looking out the audience, I'm not quite sure you're all mathematicians, but let me just make sure we understand exponential notation in the same way. So, this is 8, but I'd like you to think of it as the functions from 3 points to 2 points, okay? So, so R3 is the functions from 3 points to R, and so on. Now, if I write a stack like this, you should always read it from the top down. So I'm thinking of this as a field. This would be like a scalar field on R. And roughly, this is the Hilbert space of quantum mechanics, if you subtract all analytic detail. I'm thinking morally, we should think of this as L2 functions on R3, okay? And in the same sort of moral way, I'd like you to think of this as finite linear combinations of delta functions on R3. So this is kind of, all these are sort of models for things at the same level. So these are fields. Now what are wave functionals in this notation? Wave functionals assign a complex number to a field. So I should draw this. It's a wave functional. And I want to think of, if I think of this as the Hilbert space H, then I should think of this as the Fock space on H. Which Fock space is morally the polynomials on H. And you should think of Fock space as like one direct sum single particle Hilbert space, say the bosonic Fock space, plus the 2-particle Hilbert space symmetrized, plus the 3-particle Hilbert space, and so on. And then similarly, also another model for this would be finite linear combinations of H. Just as we have here. So this, if you think about how extravagant quantum field theory is, that this is sort of conceptually what you're supposed to think of your operators acting on it. It's something like functions of functions of functions. Since it's already so extravagant, it seems very tempting to keep going. So I would say two-way functionals are in so the usual notation for a wave function would be something like phi, and now I use something like phi with a double slash to belong to this thing. And using a model of this second type, this could be thought of as finite linear combinations of things in clock space. So it would be natural to express these two-way functionals as finite linear combinations. AI phi, but in order to do this, I put kets around the phi, a ket around the phi, meaning I don't really combine these as vectors in the previous Hilbert space. And the word I like to use for this is relinearize. You have vectors in a space, it's already a vector space, it's already a linear space, and I want to take linear combinations of them without any collapsing occurring. So I want to take these and forget their linear structure and give them new independent structure. And that can be thought of as a model for what happens every time you add a C down there. Now, I thought this idea was so crazy that surely no one would have wanted to do this before. But I gave a lecture last year at KATP on this, and several people raised their hands and said they had invented this. I don't know why they were so eager. But so I have to say that I did look at some papers and some unpublished notes, and this was discussed by Steve Giddings and Mark Shrudnicki around 1988, 1990, maybe many others. Oh, is that right? Okay. I mean, the motivation in terms of cosmology or foundations of gravity and so on is that if you have causally disconnected parts of the universe and you want to describe the universe by wave functions, once they become disconnected from each other, it's thought to be more sensible to exclude the possibility that the term should be collected between them. They should just be linearized, relinearized.
This idea of baby universe.
So I learned that these different components are associated with the idea of baby universe, and so I have a different motivation for reminding you of two-field theory, which I'll get to now. It comes from the fact that the objects of interest to me are not manifolds, but they're formal linear combinations of manifolds. So I'm going to describe kind of a growth process where things come out of the empty set. So now we're at the fourth part. Things start at the empty set, and they go through some kind of process that's very interesting in the middle, and they end at zero. Not the empty set, they end at zero. So in this ring. And with something more interesting in the middle. And the path, sort of from the empty set to zero, I want to think of it analogous as like a Brownian motion, and I want to have an action on these and integrate over them. But the Brownian paths are classical things. But the paths that I have in mind actually have linear combinations involved in their definition. They'll be formal expressions involving manifolds. So I have to think of kind of integrating over objects that aren't classical but have already been quantized. So third quantization and, two-field theory and the idea of sort of third quantized notation and so on seems to make sense. Is this board bad to use because of the lectern? It's okay? Can you see, John?
Yeah, I can see
Okay, so let me be more specific about how to link these now. So I want to think of, as I said, starting with the empty set, and go to zero, and this thing in between I'll call a formal chain. And the goal will be to write down an action with formal chains. And what it'll be is it'll be a summation over dimension D of actions which would look familiar from this causal dynamical triangulation literature in each given dimension. Plus, I think of these as kind of mass or potential terms, plus some dual kinetic terms, which say something about how amplitudes vary under small moves between metrics. And this sum a priori is v equals 0 to infinity. But I'll argue that that if you think about the sort of least action, that should cut off the sum. At d equals 4. I'll put a question mark on that. It seems plausible. Okay, so let me proceed sort of in pictures to show you a formal chain, rather than have notation with a lot of indices to sum over and so on. So, as I noted, we'll start with the empty set, and there'll be three things that we do. We can sort of grow dimension, so I'll just call that grow. We can kind of pretend there's a mirror present, and we can double. Growing will be always go from Euclidean to Lorentz in the direction of growing. And double will be double along the Euclidean boundaries. And there'll be some possibilities for fluctuations in the geometry too. So let's consider this example. By the way, growing will often an example of growing is sort of boundary inverse. If you have a manifold of bounds, just taking the thing that it bounds is sort of an example of this process, but not the only example. Okay, so suppose we start with the empty set. Suppose we want to find something whose boundary is the empty set in the next dimension. So this is the grow step. We could get a point. And now suppose we look at it in the mirror step, the double step. We see 2 points. Now, growing here, we should find a manifold whose boundary is this 2 points. And you might think I would just draw an arc, but I want to do this kind of in a Euclidean to Lorentz way. So the relative Euler characteristic has to be 0, so I can't really draw that arc. I want sort of a Lorentz manifold going this way, so that's probably the simplest example. And I'm suppressing linear combinations. I'm just taking one thing, but these could be superimposed. It's superimpose this with say a disjoint circle or something, that might be all right. Okay, then let's keep going. Let's double again. Now we get 2 circles. which I think of as Euclidean circles. See, the Lorentz structure is kind of taken to its mirror image, so it doesn't make sense to glue it together as a Lorentz manifold, but when you double, it does make sense as a Euclidean manifold now. So you have two circles, then maybe the simplest thing to grow from two circles would be an annulus. Now the relative Euler characteristic is fine, there's a relative structure here. And then when we double, we get a torus. Now there's a lot of flexibility. You know, any three-manifold dynamic torus could grow out of this, and it could grow a big linear combination. But let's just keep the example simple and grow through this causal dynamical triangulation a solid torus. Double it again and get S1 cross S2. Then S1 cross S2 can bound a whole lot of different four manifolds. But in particular, it's known, S1 cross S2 is one of the three manifolds that is known to have light-like vectors in its pairing. So in particular, it's possible for S1 cross S2, this is my picture now for S1 cross S2, I can't draw it any better. It's possible for this to bound two manifolds, sort of my canonical A and B as I've been using them in this talk, can bound some four manifold A and some other four manifold B with the property that A minus B is light-like. So now when we double, we get 0, and that's the end of this chain. Now, of course, it's kind of rare to get 0. There are lots of things in here. But if you never get 0, then the chain keeps growing and growing in dimension. And this action, is it on the board? This action, you know, will keep picking up terms and get rather unwieldy. Well, we'll go to infinity. So the point is that the only way that the action can become finite is for the, well, depending on what the various scalings are, we compare the different dimensions. But the easiest way for the action to become finite is for the chain to stop. So, so at least then there's a naive argument that, you know, actually this is formula that we had on the board as we were talking this afternoon. You know, if you have an integral e to the minus f 1 over h bar f of x, and you want to estimate this, and f is some function of the minimum a state as unique minimum, then you know, this stationary phase estimation, you know, gives e to the minus 1 over h bar f of a times some variance, which is 2 pi over f double prime k. So this is sort of what's in the back of my mind. The point is that the action for large enough coefficient in front of the action will concentrate on the places where it's least, you know, near the classical solution, so to speak. So let's say I suppressed many details, and most details I suppressed because they're not really very well worked out. I didn't tell you exactly what the about this kinetic term, which is important. Maybe I should just take 1 minute to tell you about why that's in the picture, what role it plays, why it's necessary, and then, you know, it's probably good to stop for questions. So you know, this idea that, the idea that this process would stop because of canceling requires, you should inspect very carefully in what sense these things cancel, because A and B that we're doing together are not really diffeomorphism types, they're geometries, they're manifolds with Lorentz simplices. So you could ask the question, will they cancel really as isometry types of Lorentz manifolds, or do they only cancel up to diffeomorphism? And you can actually prove that you cannot get cancellation in any dimension on the nose. You have to, it's really a property of diffeomorphism types rather than combinatorial structures. There are no light-like vectors without dividing out by the, or with dividing out by the action of diffeomorphism. So, so you have to allow some flexibility, and that's where this third ingredient to these chains occurs. So you have to allow them after you've grown A and B, or doubled, sorry, after you've doubled A and B before you grow the next level, you have to allow those, you have to have a term, you have to allow within the definition of the chain a progression from one geometry to a nearby geometry, a so-called Pochner move. And what this kinetic term that's enforced is saying that there's an energy penalty for the relative phases of the coefficients of geometries that are near each other to be very large, so that as you vary the geometry, there's some stiffness. The coefficients in the superposition should not vary too strongly. And well, maybe the most efficient way is for me to stop now and take questions.
You defined what the formal chain process is, but you didn't really define what the action is.
Well, I told you what terms it has. So it has these.
So in D dimensions, it's this reggae type action for the simplest of decomposition, or?
That's right. And of course, that doesn't tell you exactly what it is either, because each one of those is chosen from some parameter space. But it's, you know, that's what the model should be. It should be, you know, one of these tried and true causal dynamical triangulation actions in each dimension. And then there's this additional term, which I just touched on at the end. Maybe I should explain what that term's about. Would that help? So, yeah, suppose you had, you suppose this was A, just at the very beginning of the construction here. Sorry, let me, just a moment. I mean, suppose you had some combinatorial structure where everything was, the topologically A and B are the same, but geometrically they're triangulated slightly differently. So I've indicated that here. Now if you considered, okay, so sorry, there's no minus sign here. So now I take something like A minus B, and I pair it with itself. So let me just make a simpler example on one point, even though it wouldn't bodies. So there's A and there's B, and I take A minus B and pair it with itself. Then there'll be these four terms, and we'll have one bigon minus two triangles minus plus one square. So I'm just pairing an interval, kind of doubling an interval of length 1 with an interval of length 2. Considering, you know, this doubled with itself, this doubled with this doubled with that doubled with itself. So if you allowed fluctuations in the combinatorics, this could fluctuate to 0. Okay, so I want to turn in the action that prevents A and B, that penalizes A and B from entering the formal chain with radically different phases, and that's the stiffness that I was talking about, and that should be thought of as a kinetic term. Kinetic term, at least this is sort of condensed matter interpretation, like in spin theory, in spin systems. If you have a potential energy term, it's like a multiple, you know, like a polymatrix sigma z, sort of like diagonal, and then a fluctuation term like T minus T. You know, that's like sigma y, I times sigma y or something. So this plays a role of position and momentum. They're sort of dual. One is taken to the other by conjugated by Fourier transform. So anyway, that's the reason I call it a kinetic term. It's analogous to a kinetic term, and what it does is it puts me in a world where superpositions of objects that can fluctuate into each other can't change phase, but superpositions of objects that are different diffeomorphism types that cannot fluctuate into each other can have arbitrary phases. So that way I'm able to enjoy these examples, you know, A minus B, where A and B are different bounding manifolds whose difference is a light-like vector. But I don't have to worry about sort of A minus B where it's only combinatorial distinctions. So to summarize, this phenomenon of light-like vectors doesn't exist in rigid combinatorial structures. It doesn't exist in graph theory, and it doesn't exist in simplicial complexes where the simplicial structure is part of the data. It only exists in the softer world of manifolds up to diffeomorphism. So if I'm to exploit that to construct a finite dimensional least energy states and keep them in dimension 4, I have to arrange a term in the action that allows negative coefficients in the superpositions for distinct diffeomorphism types, but restricts that for examples within the same diffeomorphism type. Yeah.
In dimension 4, where you get light-like vectors, do you definitely get Lorentzian signature, or could you have split signature?
You're talking about in the pairing?
Yeah, in other words, could there be so many plus signs, so many minus signs in your signature?
So let me just make perfectly clear, I understand what you're saying. You're asking about the pairing of the universal TQFT, not the space that's being built.
Right, right.
Yeah. Actually, I think that question doesn't make sense because I'm actually slightly abusing notation when I call the pairing positive or light-like. This isn't a Hilbert space with a real inner product. The terms positive and light-like mean actually nothing more than what I wrote. That it's positive if this implies that. I could have equally well said negative. And then light-like just means that you have a non-zero V that paired with itself is 0. A good question, though, about these abstract pairings, and something we don't know the answer to, is whether they have any singular vectors. It's an open question in any dimension, whether you could have a non-zero vector V such that VW is equal 0 for all W. Excuse me.
talk about diffeomorphism between the Lorentz manifolds. Can you really throw away the Lorentz structure completely, not leave any trace of it?
That's a good question. I think that because your question is if you have diffeomorphic Lorentzian manifolds, are they diffeomorphic taking positive cones to positive cones or something like that?
That might be too strong of a restriction, but at least you could ask that some positive vector goes to a positive vector that goes to a positive vector.
Right, right. I think that in terms of extending the Lorentz structure, the only topological obstruction is relative Euler characteristic. It's basically the positive direction should be non-singular. So that's their existence, and you're asking the uniqueness version of this question. So I'm not sure. It's a good question.
I have some questions in higher dimensional manifold theory, how we can be decided. Can you tell if we're a given combination? This is not automatic.
No, I think it probably is undecidable. I mean, yeah, I would think that, I wouldn't expect that there'd be any algorithm I mean, when this problem comes of collecting terms, I mean, even settling the question whether two terms have the same fundamental group is probably undecidable. But I don't think anyone has to decide.
But presumably all if it's like transassignments, the physical, topological, quantum theories, do we decide the questions?
In 3 dimensions?
That's true, I don't think three, formally, if I have a local action, physical definition,
Yeah.
there's no modified definition to decide.
Well, I mean, it might be that the decidability comes in this way, that if you have terms that cancel out, but you need non-recursively many Hockner moves to get from one, to see the cancellation. So say, like I gave this example where I said you have these 4 spheres and they do cancel out, and in this case, each one is given by a small number of handles, and the number of moves is actually a small number of moves to check that they're the same. But suppose and those moves should be thought of as fluctuations, okay? Now, suppose if it's undecidable, if you have an undecidability problem, if it's undecidable in general whether these are in the same diffeomorphism class, what that means is that for concrete examples, there will be cases where they are equivalent by moves, but the number of moves is not a computable function, right? Well, even if the number of moves is just extremely large, set aside non-computable, in some sense it might not I mean, I kind of get the drift of what you're saying. You're saying suppose these different terms cancel out mathematically, but it's so hard to discover that they cancel out that the universe keeps growing in dimension because it didn't notice that they cancel out. Yeah, I think that's a very interesting question. I hadn't thought of that. Yes.
I wanted to make a comment that I remember Arnold made about the question about uniqueness. He made this interesting comment. Take two closed four manifolds that are not diffeomorphic, but they're homeomorphic, and then cross with R, and think of the causal structure on each one, that still remembers the four manifold, because any positive vector field, the cross-section will be there, but when you cross with R, they'll be all diffeomorphic. So all of those examples would give non-unique, a whole bunch of different Lorentz structures. The dimension 5
Right, right.
was a remark of Arnold's
Yeah, I see.
a long time ago.
I see. Yeah.
So is that really right?
Hmm?
I mean, if you only have the positive cone that you're worrying about, do
Yeah,
all
but I
vector
think
fields
you
in the positive
transversely
cone give the
see
same
it.
cross-section?
I think so.
I guess the vector
Any
fields are all
positive one would be
homotopic.
transversal.
The vector fields are homotopic. I see.
I see if there's a Lorentz isomorphism between these manifolds, then you could, then their time, then the cones would be, no, actually, yeah, I'm actually having trouble with this argument too, so.
Something.
So if you have a vector field, all the cross-sections are diffeomorphic. Just flow up to a higher one. Right?
Right.
And now if I vary the vector fields smoothly, the cross-sections stay diffeomorphic by continuation.
No, if you keep the vector field in the cone, it's always transversal. The same manifolds are transversal. In other words, the transversals are well defined to diffeomorphism. Any two transversals to a vector
Yeah.
field are diffeomorphic.
Yes,
That's all I.
but now I have two different vector fields, both in the positive cone. Oh, I see. So
But they're both transversal to
transverse
the same foliation.
Well, thank the audience too for your thoughts, thank you.